here we'll be talking about this idea, this class of methods, which we call multi-iteration stochastic optimizers, which are methods for solution of stochastic optimization problems. So I will start discussing the problems that we are trying to solve, the class of problems. I will discuss briefly what is the stochastic gradient descent method, and then I will follow with our method and some numerical examples. Okay, so what is the stochastic optimization problem? Well, for a vector here named psi of optimization variables, and for a vector of random variables theta, a stochastic optimization problem in this classic form would be to find psi star that minimizes a function named the objective function. And here in this case of stochastic optimization, the objective function is given as an expectation of another function, here named as small f, condition on psi. So in deterministic optimization, if we have access to the gradient of f, we can converge to psi star. However, what can be done if we can not observe the gradient of f, but just the gradient of small f? Well, this problem is very relevant in many fields. And another variation of this problem that we are interested in is the problem of minimizing a finite sum. This is specifically interesting for machine learning people, because usually they have some data and they're trying to minimize some function with respect to this data. We will be solving both problems and discussing them specifically when it's convenient. So,
André, I'm sorry to interrupt you.
okay.
In equation 2, should you also
Okay.
write arc mean? You know, I have feelings that arc mean is lost.
Here, arc mean is here.
Here, yeah, this first equality I understand, but second one, you know, I do not understand how arc mean
Yes,
problem is
I
equivalent.
understand. There is some confusion here because, let's say, f is defined as yes. I'm trying to find the argument of this whole thing, which is defined as f. Okay, I agree that this is not clear. I should have tried to make things shorter and make a bit messy. But you're right, Alex. You're right. This is not consistent the way it is written. But yeah, we are trying to minimize the sum or the average of functions here. This is a problem we're interested in. And what assumptions we will be making for our analysis of f? Actually, the average, the expected value is that it is Lipschitz continuous. The gradient is Lipschitz continuous, so it's smooth, and that it is strongly convex. So this will be used for the analysis, but our methods in general do not require these assumptions about the objective function. So let's talk about stochastic gradient descent briefly. Well, the idea of stochastic gradient descent is to use not the gradient itself of the objective function, but some unbiased estimator, here named epsilon. So if we can sample theta from this distribution, and we have access to this unbiased gradient estimator, we can perform optimization and converge to psi star by taking steps on the direction given by the gradient estimator. Given that, we decrease the step size. And this is the thing with stochastic gradient descent. This decrease of step size is required to deal with the noise that we have, the difference between the estimate and the true gradient. And given that we have this decrease in step size, we end up having less than ideal conversions. Some ideas to deal with the error in the estimate of the gradient, the difference to the true gradient, is to use, for example, mini batch sampling. Well, where instead of just using epsilon here as nabla f, which is the idea of vanilla stochastic gradient descent, we use mini batch sampling, in which we sample not just one, but here small b, theta I, and then we use this average as our gradient estimate. Of course, here we see that we are reducing the variance component-wise by b at the cost of increasing the cost per iteration by b. So this is what mini batch sampling and stochastic gradient descent are. So as I mentioned before, since we have to decrease the step size each iteration to deal with the uncertainties, even if we use mini batch sampling, we still have to deal with this sublinear convergence here. Now here I'm presenting deterministic steepest descent, where we have the linear convergence, and for stochastic gradient descent, we have sublinear convergence. Now, more also, we see that for this situation, we cannot parallelize as efficiently, because even if you're using mini batch sampling, we can only do it for this mini batch B. And in the next iteration,
Okay, so did we lost André, or it's my problem?
have to increase the sample sizes here, the mini batch sizes. And this is the idea of stochastic gradient descent with adaptive sample size. Now here I am presenting V, second moment norm of the gradient nabla F, right? So if we use a sample size that follow this rule, where this is a parameter to be defined, then we know that in the L2 sense, we'll be having a decrease of the objective function that will behave as this exponentially convergent sequence here, which means in optimization terminology, we'll be saying that this method converges linearly. And with a fixed step size, which is really important. Now, this idea is not new, is around kind of like 10 years now, different ideas revolving around these and step size and sample sizes. And it has some advantages, some disadvantages. The advantages are linear convergence, of course, and that as you increase the evaluations of nabla-F per iteration, it will be easier to parallelize things. We'll have larger bulks of gradients to be evaluated each iteration, and we can do things smarter, in a smarter way. Now, of course, the drawbacks are that this will grow really fast. The number of iterations, I mean, the number of sample sizes that we need. And more than that, the biggest problem here is actually that we need the true gradient norm to evaluate the optimal sample size. And we don't know that. Actually, it's quite hard to estimate since this quantity will be converging as iterations go. So we're getting closer and closer to zero. It will become more complicated to get a good estimate. Now, there are some other ideas to control the variance without necessarily increasing the sample size, like using variance reduction techniques. And the best known is to use control variates. And the idea here is that if we are trying to look at the expected value of some random variable, which is correlated to some other random variable that we happen to know the expected value, then we can perform control variates and get a better estimate with smaller variance, here denoted by Z. So in optimization, this is equivalent to do control variates component-wise, given some gradients that is already known. For example, we evaluate this as some size 0, and then we can, in subsequent iterations, perform control variates with respect to it, and thus having a gradient estimator with a smaller variance than this one. So the best known method for this class is the SVRG, which is around since 2013. And it's developed for the finite sum case, right? So we sample each iteration our thetas, and we do contravariate with respect to some iteration where we perform the whole sum here, where we got the full gradient. Now, once in a while, we have to evaluate the full gradient once again, and we perform the steps as presented here. And this method is known to converge linearly also for this class of finite sum minimization. And here I am presenting also other methods that are of the same family. And here we have the conditioning number and the number of functions that we are minimizing the sum. So maybe we can do better than this for the minimization of expectation. And this is our idea. So now I will present mice, which is our gradient estimator. So the idea of mice is to build a hierarchy of iterations, and then we will sample from this hierarchy of iterations and use contravariates between them to try to get a gradient estimator at the current iterate with the variance with statistical error that is acceptable, that we want, with the smallest possible gradient sampling cost. So this gradient estimator can be coupled with any first-order stochastic optimization method, and they will result in this class of optimization methods, which we call multi-iteration stochastic optimizers. So how does mice work? Well, we define the hierarchy here as the set of indices from 0 to k at iteration k. We use this because we will not want to keep all the indices here from 0 to k. We might want to just keep some of those. And then from these items in the hierarchy, what we do is we have these deltas, which are differences of gradients between components or elements of this set. And we will have, for the first of component of element of the set, we will have here that this term doesn't exist. So the delta 0 here will be just the gradient evaluated at the start, and all the other deltas that we have will be kind of correction terms, will be differences of gradients, in a similar fashion as in multi-level Monte Carlo, that I believe that most of people here are familiar with. So these deltas, we will be sampling alpha as I previously shown, independently from one another. And also we will be sampling for each level this alphas and the thetas independently. So the levels are independent, and it's easy to see that the expected value of this estimator in principle will be the expected value of the current iterate. Now here I'm trying to illustrate a bit better what is happening here in the case where we have all of the levels and we are just summing these differences, and an expectation it cancels out, and we keep the gradient at the current iterate. So the trick here is, how do we get these sample sizes? We want to control the statistical error of this estimator, and we want to sample the sample sizes that we will have for each level in the best way possible. So how do we do that? Well, let me discuss how it works in these illustrations. Well, let's say that we start at x0, we sample have a sample of size m00, and we perform a step to x1. Then what we do is to sample the difference between here and here with size m11, and we sample more at at our x0 here. So the whole idea is that we don't only sample at the current iterate, but we go back and we sample more from the past. And then we use control variates here represented as this dashed line to get a variance reduced gradient at x1. And we do this sequentially. So we will keep sampling from not only from x2, but from the difference between the gradient in x2 and x1, and then from x1 to x0. And this is the idea of our method. So to know the sample sizes, we need to have some idea of the statistical error of our estimator. And here the statistical error of our estimator is given as the sum of the contribution of each level that we have in the hierarchy, where here V is given as the sum of the variances component-wise of the difference between the gradients, which we observe from the data that we have. And here we see that the sample sizes appear since we're looking at the average here, right? The average of the deltas. So now we are posed with the problem of how do we choose these sample sizes in order to keep the statistical error of our estimator below our threshold. Well, so for that sake, we define the sampling cost of our estimator, which is the sample of all of the gradients that we need to evaluate. Here, this indicator function is a simple, it simply indicates that we are or not in the bottom of the hierarchy. So if we are, the cost of sampling is just 1. If we are not on the bottom, then we need to sample 2 gradients because we are computing differences. Then what we want is to find the sample sizes that minimize the sampling cost, subject to the constraint on the statistical error of the estimator. And this is what we get. We get a closed form solution for the sample sizes for each level at iteration k, given that we have these VLs also for each iteration k. And also for the finite sum case, here we have a finite sum of n functions. Here we have this similar formula. Now, if we follow of this, we recover the linear convergence of the deterministic methods, similarly to the stochastic gradient descent with adaptive sample size. At least for this class of L-smooth and strongly convex problems, which are the assumptions that we are making. Now, this might not be the ideal, not the best that we can do to keep all of the iterations in our hierarchy. We might want to choose which iterations we keep, which iterations we discard. So we have these operators of the hierarchy, which will be used to choose the best hierarchy in some sense. So how do we choose the hierarchy? We will be comparing not only the sampling cost, which is this quantity here, with the cost of multiplied by the cost of each gradient, nabla f, as also we'll be looking at the overhead that we have as the length of our iteration of our hierarchy increases, which is this quantity here. Noting that these constants here, we can measure them on the fly. So we will try to see what is the hierarchy that minimizes the increase of the total work here. So the first operator that we'll be looking at is the restart operation. The idea is straightforward. Sometimes it might be advantageous to just discard everything that we have and start from scratch. So here we have the cost of restarting, which is the same as the stochastic gradient descent with adaptive sample sizes. So if the increase that we have in the work at iteration k is larger than the cost of restarting, then we restart. Here we have a parameter that favors restarting. And so to better illustrate the restart operator, so we are here, we take a step to here, and it might be that it's better to just restart and discard this point here and not use control variance. So the advantage of restarting is that first will never be worse than STD with adaptive sample size. And at the worst case scenario, we'll be restarting each iteration, which will recover the cost of SGD with adaptive sample size. And more importantly, we'll be reducing the overhead, as will not allow the hierarchy to get too long. Also, we force restart if the hierarchy gets too larger than a fixed value, even if we do not satisfy the condition before. And now the second operator that I will present is the dropping operator, where we check whether or not to discard the previous iteration that we have in the hierarchy. So here, to do that, we compare the V as I presented before, but V bar here represents the variances component-wise sum between the difference of the gradient now and not the gradient that we have previously, but the one before. So if this is smaller than this, then we discard the previous iteration from the hierarchy. And here also we have this parameter that favors dropping this iteration. And later I will show you that in many cases, we actually end up dropping more iterations than we keep. And so this operation is really, really important for our method. So to illustrate this, here I am presenting an example, say that we are here, and now we have to decide what to do here to take a next step. And if, for example, the correlation between the gradient in x2 and x0 is better, say, than the one going from x0 to x1 and x1 to x2, then we just drop x1 out of the hierarchy and do control variance directly from x2 to x0. So the last operator that we have for the hierarchy is the clipping operator, where we check for some level here noted as L prime in the hierarchy, if it would be advantageous to just discard anything that is smaller than L prime. Just keep what is the components of from L prime onwards. And to do that, we check for each L in LK whether or not the increase in the work would be the smallest possible. And the best case is what we keep. So to illustrate this, let's say we have the situation, and if it's advantageous, we will just clip it here and throw a x0 away. Now x1 is the bottom of the hierarchy. So these operators, they are very important, as I mentioned before, in both reducing the gradient sampling cost, as also to control the overhead that we have both in terms of memory and processing. So now the last thing I want to talk about our method is this idea that we use, which we call resampling, which is necessary given that we don't know the norm of the true gradient. As I mentioned before, for the adaptive stochastic gradient descent, we need to estimate this quantity to set up the optimal sample size, but we don't know it. And as iterations go, this quantity converges to zero, and we are faced with the problem of estimating this quantity, given that we have observations nabla f which do not converge to zero. So it gets more and more difficult to get a good estimate as iterations go. So what we do is we do this resampling technique in which we try to build some probability distribution of our estimator of the norm of the estimator, actually, by doing some techniques that resemble jackknife sampling. So to illustrate this, say that we have the set of of deltas here, differences of gradients at level L. And for each level L, we create copies of this sample. And for each copy, we remove a fraction of the samples from it in such a way that these parts that we remove are complementary and they sum to the whole set and they are of the same size. Then once we've done that for all the levels, then we sample from it uniformly. Actually, for each level, we sample uniformly one of these sets, and we use them to get some estimate of our gradient estimator. Here denoted with nu. So we do this several times independently, and at the end we have some idea of the norm of our estimator here, for example. Then once we have this, we can choose some percentile, which is a parameter to be set. Obviously, the smallest, the more conservative we will have of an estimate of the norm of the gradient. And then we use this as in place of the norm to take decisions. For example, instead of controlling the statistical error to be smaller than norm of the gradient, we use these quantities that we get from the resampling. Then, of course, this adds some overhead, but it compensates in robustness of the method, as we will see soon. Now let's look at some numerical examples. First is a very simple quadratic function where we have some randomness here in the hashing. So we have here this matrix, which is an identity, and this other matrix where kappa is a parameter.
One question, André. How many resample gradients you usually use?
We fix a percentage of the effort. So we for example, we say 20% of the whole cost. So we adaptively sample in such a way that we never sample more than 20% of the total cost. That's how we do. So we do not let the cost of resampling dominate the total cost of the method.
Thank you.
We also have a minimum and maximum value. So there are a few parameters to be set there. I didn't want to get too much into the implementation details and things like that, but this is what we actually do. I made a remark about it in the conclusion, but thank you for asking. So back here to this numerical example, this quadratic function here. So here we'll be comparing our method SGD mice, SGDA, which is how we call SGD with the adaptive sample size, and just plain simple vanilla SGD with just one sample. So first, let's look at the convergence of our method SGD mice. Here I'm presenting the optimality gap, the distance to the optimum, and the norm of the estimates. We can see first that we have a really nice looking linear convergence for this example. Even this estimator being noisy in the sense that it's not the true value of the gradient that I'm presenting here. We can see that there are some oscillations, but they are not dominating we can see a really clear pattern here of convergence. Also, I am presenting you restarts as squared red squares here and dropping small x's. And we can see very clearly that most iterations are dropped out of the hierarchy, keeping the hierarchy short and keeping the overhead relatively small. Moreover, we can see the expected rate here of convergence, the one that I presented before, and we can see that we are really close to the expected convergence rate of the method. Now I will present the same quantities except versus not the iterations, but the number of gradients. And here we can see something that we could not see before, which is a change of regime around here at 20,000 gradients, which is actually when we achieve the tolerance of the statistical error, and we need to start to increase sampling. So then we get to the regime where we have an increase on the sample size each iteration, which follows the expected convergence rates. And yeah, I don't want to spend too much time here. So here I am presenting the error that we have, the relative error actually, each iteration. And here you can see also the tolerance, the epsilon, the parameter that we set as 1. And here you can see what I talked about before, where we had a relative error that was smaller than the tolerance. When we achieved here, then we started sampling more. That's why we got the change of regime before. You see that we automatically started to follow the rules of sampling more. And also here I'm presenting the length of the hierarchy, and we see coinciding here that we start to drop less iteration. I mean, we still dropping most of the iterations out of the hierarchy. Then it's once in a while we see that it's advantageous to keep one or another, but still at the end of the optimization, we were at 11 iterations in the hierarchy out of 1,200 more. So we can see that we end up dropping, I don't know, more than 99% of the iterations. So here I'm presenting the optimality gap versus iterations, the number of gradients for stochastic gradient descent, and the other methods, stochastic gradient descent with adaptivity and stochastic gradient descent wise. And it's important to note that we even use the resampling idea to level the field for SGD adaptive, but we still were not able to get smooth conversions as we got for SGD mice. So in general, what we can say about this example, what it tells us is that SGD mice works as expected. We got the rates that we expected. We got better results than vanilla SGD and SGDA, and that our operators worked as expected, keeping the length of the hierarchy short, and as a consequence, the overhead. Now let's look at very briefly to another example, which is one that doesn't satisfy the assumptions that we made before. So this is the goal of this example, is to show that we can not only couple mice with SGD, but also with mice or any other method that you might want to use as a stochastic first order optimization method. So we adapted the Rosenbrock function, which is really well known in deterministic optimization for this stochastic setting where we have some randomness here on this theta random variables, which are Gaussian distributed. And we will use Adam and Adam mice and compare their performances. Now here is a contour of the function, which you can see that is non-convex. Actually, it's really hard for first order optimization methods like gradient descent to solve this problem, because you have this whole region here where the gradient norm is really close to being 0. So the steps are really short. So if you start here as we start, then in general, first order methods struggle to get here. Now, Adam is good for this kind of problem because it adaptively takes larger steps when it realizes that it is needed, that second moments are small. That's why Adam is called Adam, from adaptive moments. And that is why we use this method for this problem. So here we have, for one case, both Adam and Adam mice. And we can see that Adam mice was able to consistently approximate the optimum and reduce the optimality gap. And in terms of iteration, it's quite clear that it took less than 100 times less iterations than plain Adam. And here, of course, runtimes they are always implementation dependent, and these were all my implementations of these methods. But still, we got a huge advantage from evaluating many less iterations and sampling more at each iteration. And we can also see that pure Adam, even with decreasing step size, which we used here, still started to wiggle around the optimum, which is something that we avoid by using mice and controlling statistical error of the gradient estimator. So in general, these are the conclusions that I just mentioned. We needed 100 times less iterations and 1/4 of the runtime for my implementation on this problem. And let's look to our last example, which is one of minimizing a finite sum. So here we have a logistic regression model with L2 regularization for binary classification. And we'll test the training of this model for 3 different data sets with different sizes and different numbers of features. Now, it's interesting to note that this data set is huge. It has 11 million points. And a number of features will be the number of variables that we have in optimization, the weight of each feature, which is what we're trying to find. So the first data set, the mushrooms data set, we observed an improvement in terms of number of gradients. We converge more per number of gradient. This is the relative optimality gap. And also in number of iterations, but again, runtime wise, which is implementation dependent, we did worst. And this is somehow expected since we add a lot of overhead calculating variances and all, and this objective function is actually quite cheap. It's just few matrix vector multiplication, actually vector multiplication. So for this case, we didn't improve in terms of runtime. Now for this other data set, which is one that has even larger number of features, so we have 6,000 variables here to optimize. Still, we did that better than the other methods that we compared with, which are the ones for minimization of sum using control variates. Especially in terms of iteration, we did quite well. However, in terms of runtime, again, we did not impress in comparison to these other methods. And however, for the last data set, which is the Higgs data set, then we were able not only to beat the other optimization methods in terms of number of gradients, as also in number of iterations by a whole margin here, 3 orders of magnitude less iterations, as also in runtime. Why? Because this data set is is huge, 11 million points, and these methods, they suffer to deal with this, with big data. So the overhead of mice pays off in this case, at least in my implementation. So the whole goal of this last example was to test our method in finite sum setting and compare it with other contravariate methods, which are quite standard in this kind of problem. And in all cases, we got better optimality gap per gradient evaluations. However, for the first two data sets, we didn't perform as well in terms of runtime, but for the third one, where we had a large data set, then we got the best out of it. So in conclusion, we can say that it's advantageous to use mice, especially if you have larger data sets and small numbers of features. Okay, so in conclusion, today I talked about our class of stochastic optimization methods, where we use mice as a gradient estimator, and where we can reuse information from previous iterations. We sample adaptively in order to control the statistical error of the gradient, allowing us to converge linearly in some classes of problems. Also, we can use mice not only to minimize expectation, but also finite sums, specifically being advantageous for finite sums of large numbers, large data sets. Also, yes, SGD mice in the strong convex setting recovers the deterministic linear convergence. So mice overhead, again, might not compensate if the objective function is too cheap. But as the cost of sampling gradients increase, mice get more and more interesting, more and more advantageous as we usually require, we can converge with less gradient evaluations. Now, some things that didn't make it, and I think are important to mention, are that we do not store all of this in our implementation. We just store some summaries. We keep the mean and we keep the V's, and we update them online using Welford algorithm. Not only for these deltas, but also for the ones in the resampling. And also, as Luis asked, and I mentioned before, we adaptively control the resampling size by keeping it at maximum as a proportion of the total work. So that we don't allow the resampling cost to dominate the whole cost of the optimization procedure. Now here are the references. So the articles of stochastic gradient descent with adaptive sample sizes are on paper. And these are works where contravariate variance reduced stochastic gradient methods. And that's it. Thank you very much.